Okay, so this lesson is the beginning of chapter 7. This word is stoichiometry. Often we are going to short form it as stoic. So in order to save paper and not have a piece of paper with one slide on it, I did not include the title. So if you want to pause the video quickly and write down the title of stoichiometry, then you can do that. This is the start of chapter 7. So the next assignment we have will just be on chapter 7. Okay? So stoichiometry is the study of relative quantities of reactants and products in chemical reactions. So what we all want to be able to do is, if you have a balanced, that's important, chemical reaction, we are going to relate the moles of one substance to the moles of another. So basically all the topics in this section will be applying the mole concept. So unlike the last section, or chapter 6, let's say it said 5 grams of oxygen, then you would have found the grams of oxygen, or even the applications, 5 grams of oxygen in a sample. So you would have done 5 grams divided by the molar mass of oxygen, and then found the moles, and then maybe done the mole ratio. You didn't, or to divide by the smallest. You didn't have to worry about how that related to something else. So when you have stoichiometry, it's like the recipe. We are looking to compare ingredients, for example, reactants, in order to get the product we want. So when you're in grade 10 and we first talk about types of reactions, we don't really worry too much about teaching you about will a reaction occur. So we've already looked at cases qualitatively, like using the activity series, can a reaction occur? Using solubility guidelines, can a double displacement reaction occur? Reactants also have to have the same amount. You can't just randomly throw a little bit of a compound in and expect a reaction to work. So if a grade 10 teacher comes to me and says, can you help me make a solution? I'm trying to get a red precipitate. I have to ask them questions about what's the concentration, which is what we're going to do next, or moles per liter of solution. And because it's not just enough to say insoluble or soluble, we also have to look at the amounts. So moving forward, we're going to look at we're going to continue with this intro to quantitative chemistry. Then the next big unit will be solutions and solubility, and then acids and bases. And then after that will be gases and how amounts in the atmosphere affect us, which is actually huge right now because the coronavirus is changing the concentration of some gases that we don't want in the atmosphere. Okay, so the amount is going to be much more important than is it just there. So we're going to, again, leave behind qualitative and use and focus more on quantitative. So yes, we balance chemical equations because of the law of conservation of energy. Mass. Mass cannot be created or destroyed. You cannot just create something from nothing. So we use coefficients in order to balance the same number of atoms and same number and type on each side. Now the coefficients are going to tell us in general how many moles of each reactant you need in order to predict how much product you're going to produce. So in math, you talk about ratios like a 1-to-2 ratio. Maybe you have a job where you need to clean at the end of the night. And often when we buy cleaners, it'll say like 1 part bleach to 3 parts water. That is looking at a ratio and essentially doing stoichiometry. You buy those concentrated orange juice cans, 1 can for 1 to 1 liter of water or whatever. That's what we're talking about here. Trying to figure out the ratio. Okay, so the ratio of one chemical to another, and it actually doesn't matter. You can be given the products and figure out the reactants. You could be given one reactant and figure out both products and the other reactant, how much is needed. So moles and the quantitative side of chemistry is so useful. And as long as you can get behind the concepts, it's actually pretty straightforward and logical as well. Okay, so again, we're looking to calculate. We want to know exactly how much we're going to get. Okay, so let's say we have this equation here. 2H2O plus O2 makes 2H2O, so it is balanced. There are 4 hydrogen atoms on the reactant or the left side and 4 hydrogen atoms on the product side. 2 oxygen atoms on the left because oxygen is diatomic, and then on the right-hand side, oxygen, there's only 1 oxygen in water, but because of the coefficient out front, we multiply, so you get 2. So if you were talking about this in terms of the ratio, then you would say out loud, 2 moles of hydrogen gas, where does that 2 come from? The coefficient is needed to react with 1 mole of oxygen gas. So even though we don't write the 1, it's understood. And you will get 2 moles of water produced. So this ratio is 2 to 1 to 2, okay? And so that's fine if you have 2 moles of hydrogen gas and 1 mole of oxygen gas, but what if you don't? So then you can calculate it, like I said, pretty straightforward and logically using the mole amounts you have. If we react 0.6 moles of O2, how many moles of hydrogen would need to react and how many moles of water would need to be produced. So we can take the one value we're given and convert it in, as long as it's moles, and convert it into any of the other reactants or products. So if you'll notice, we have moles. So there are, if you choose to print the worksheet off, there are questions at the beginning that already are moles. And then, so we'll do an example here like this, and then we'll do another example where you're actually given grams. So then the first step will, in the calculation side of things, will be to change grams into moles. We are never going to compare grams, okay? So how do we do this? So you can write a ratio, and sort of surprisingly, sometimes in math, in the applied stream, there is actually more curriculum of ratios, rates, and proportions, but that's okay. So normally we do sort of a variation of this one. Now, normally, because we are English readers, I like to do mole at the top because normally that's what we're looking for, but it doesn't matter as long as you have it on both sides, okay? We are English readers, so we start on the left. So I like to put my unknown variable on the left here. So normally we're looking for some kind of mole amount given another mole amount. So if they're here, in this case, there are 4 parts to our ratio. That means that we need to know 3 out of the 4, right? You can't have more than one unknown. So then down the second one, the coefficient, you could do this as well. So it's coefficient, and then mole amount, A in the top, B in the bottom. But like I said, normally we'll use the first-ish version. And if you are the kind of person, you can certainly write these as rates of change. So you can do, let's say we're looking for the mole of A. That's our unknown value. And we're given, then we would have, you want to make sure that you are able to cancel it out. So then you would multiply by the coefficient of A by the rate of change. Oops. But you'll see once we start to rearrange that this is essentially what you're going to get anyways. But if you like rates of change, you can certainly write it like that too. But I'm going to use this the most, okay? Right here. Okay, so now back to this example. If we react 0.56 moles of oxygen, how many moles of hydrogen would need to react and how many moles of water would be produced? So when you have this, then we're going to set up a ratio. Okay, so we are looking for the moles of hydrogen. So right away, we can put in an unknown variable. What's the most common unknown variable we use? X. So how many moles of hydrogen? And then once you've decided that, it actually basically sets the rest of the ratio up. We have moles in the top. That means that we need to put moles in the top of our fraction. Okay, so we have mole, mole, and in the bottom, we're going to put, since this is H2, we're going to use the coefficient of H2, which is 2, and then the coefficient of oxygen, oops, sorry about that, which is 1, not a 7. I realize these are very simple ratios, but they don't always have to be. And next year, what we're going to do is we're going to use this and apply it to how much energy is in a reaction, how fast a reaction goes, what's the rate of reaction. So building the ratio is an important step. Okay, so let's go over it one more time. Why did I pick X moles of hydrogen? That's what the question asked me. What was I given, right? So once you have the unknown, that's it. You can't have any more unknowns, okay? So I have to use what I'm given. What am I given? 0.6 moles of oxygen. So I put that here. And then in the bottom are the coefficients. Where did I get those? The balanced chemical equation. Okay, so now you have some choice. So again, this is basically the rate of change, 0.56 divided by 1, and then times 2. You can think of it like doing the inverse operations. So 0.56 divided by 1, and then multiplying by 2 to get the 2 out of the bottom of the fraction. Or you can do cross multiplying, which, to be honest, is probably moving forward going to be the easiest. So X times 1 and 2 times 0.56. Okay, so again, you can kind of check the logic of your answer. If we have 0.56 moles of O2 and we're going to use twice the amount, then it makes sense that it's 1.12. That is twice the amount of 0.56 because the basic ratio is 2 to 1 to 2. Okay, so then same thing here. So now, since water and hydrogen have the same coefficient, then they have to have the same mole amount. Okay? But let's do the math to prove it. So now this time, what am I looking for? Moles of water. So that dictates what my X value is. I have to use what I know. You can use the one that you calculated down here. It doesn't matter. And then you put their coefficients at the bottom. Okay, so again, 1 times X. And 2 times 0.56, 1.12 moles of H2O, which I could have predicted because I know it's 2 to 1 to 2. So if they have the same coefficient, they can have the same mole amount. Now, would they have the same amount in grams? No, they wouldn't, right? They would take up a different amount of space, which is why we never use grams. Grams is based on how much space something takes up. Moles is all based on Avogadro's number. Okay, so when you have a question, you must have a balanced chemical equation. You just saw that in our ratio, we're going to use the coefficients. And you must have mole amounts. So if you forget how to do everything else, if you change grams into moles first, you'll at least get part marks. So if you are a formula person or a triangle person, it really doesn't matter. Okay. So the question we're going to do now is a beefy example, and you're going to see how much you can do with very little. There we go. Potassium chlorate decomposes to give oxygen gas and potassium chloride. So I am going to, this question does everything. We have to do the crisscross rule. We have to remember diatomic molecules. We have to balance all of it. Then we're going to do how many grams of potassium chlorate must be decomposed to give 0.96 grams of oxygen. Okay, so that's B, how many moles of potassium chloride will be produced, how many molecules of potassium chlorate are decomposed, and how many molecules of potassium chloride are produced. Actually, I don't know. Okay. So let's write a balanced chemical equation first. So when you do this, you have to, again, do the crisscross rule. So potassium chlorate is potassium. Chlorate is the ATE, right? Means it's on the back of the periodic table. So when you crisscross, we're not going to be super stressed about states for now because we're really trying to get the quantitative stuff down. And then it says decomposes to give oxygen gas. So you do need to remember that oxygen is diatomic, and potassium chloride. So we have potassium and chloride ion, also both ones. So when you crisscross, the ones cancel out. Okay, but this has, again, maybe you can do it by inspection. It really doesn't matter. But when you look at this side here, oops, what am I doing? Sorry, that's not, I'm just gonna scribble it out. There are 2 oxygen atoms, which is not good, okay, compared to the 3. So I'm gonna make this even, which is gonna change this to 6. I like that. That's easier to balance. Makes 2 potassium and 2 chlorines as well, but that's easy to fix because they're in the same compound over here. And then the oxygen we need to make even. No problem. KClO3. 2 KClO3s makes 3 O2s and 2 KCl. So now it is balanced. We're good to go. And then when you set up your questions, I really recommend that you write out the equation and then you have a line on your paper for M, which is mass, a line on your paper for MW, which is molar mass, and then a line on your paper for moles. Because similar to the empirical formula chart, now moles is mass divided by molar mass, right? So this line divided by this line gives you the next line. So that makes things sort of nice, okay? Also, it helps to organize your information because what are we given in A? We are given, let me just check something. So I'm gonna write in here. We're given 0.96, okay? And we are asked for the grams of potassium chlorate. Okay, so in order to do grams, we can do molar mass, no problem. Okay, so when you do the molar mass or molecular weight, I'll write it as a little aside down here. Actually, just let me check something. You want to make sure that the molecular weight you don't multiply the coefficients, okay? Because we're going to do that later. We're going to use those in the ratio later. Okay, so that's how I got that. So normally in order to find the mass of potassium chlorate, you would need the moles, which we don't have right away. So that's where this oxygen mass and the mole amount can come in useful. So now over here, it's going to be 2 oxygen, which is 32. So we can easily find the moles. When you do this, you can decide, again, how many decimal places you want to keep. It doesn't really matter on a paper pencil task. Okay, so now we have the mole amount of oxygen, and we need to convert it into the mole amount of KClO3. I was hoping to get a different color. Let me just see. Okay, so we need to convert. Okay, so I'm going to write a little note. So we're going to take this and change it into the moles of KClO3. And what is the procedure to do that when you're converting moles? It is called stoich. Okay, so we are going to write a stoich ratio and do that. So again, choose the way you want to do it. But now, since we are looking for this number here, again, what's the most common unknown? X. So how many moles of KClO3? We have the moles of oxygen. Sorry. And what do we put in the bottom? The coefficients, the 2 and the 3. Okay, so now these ratios are not perfect. I'm really sorry, guys. I'm going to finish this out up here where I have space. Okay, so the 3 and the 2, now it's easier to do the cross multiplying. X times 3 equals 2 times 0.03. Okay, so to get rid of the x, or get rid of the 3, you have to divide. So 2 times 0.03 divided by 2 is 0.02. Okay, so now we have used stoichiometry and changed or converted the moles of oxygen, which we were given the grams for, into the moles of KClO3, because that's what the question has asked us. And now we're going to find the mass. So some people, when you get used to this and you're, a whiz at it, they'll just actually do the math and put the mass right in that spot there. You can certainly do that, but I'll, for this note, I'll just write it on the other slide. So however you choose to do that, with the triangle or with the formula. If you always leave it like this, you can plug in the numbers. It actually doesn't matter. Okay, so now we have the 0.02 moles. We already found the molar mass, which is why the chart is so useful. 2.45 grams of KClO3. Okay, and now we've done a lot of work for A. So A would probably be like 6 marks, but then B and C and D would be like 2 marks, because now we can use the mole amount of oxygen or the mole amount of KClO3, it actually doesn't matter, and convert it between all the other substances, which is why moles is so useful. Okay, so how many moles of KCl are produced? So how many moles, that's our X, how many moles of KCl over its coefficient, and we have the I'll just use the moles of oxygen. Most people, for whatever reason, maybe you don't trust yourself, you always go back to the one you're given. Okay, so again, KCl and KClO3 have the same coefficient, which means they are going to have the same mole amount. Read the question carefully. This one does not say that we have to change it back into grams, so I'm not going to do that. Just leave it as moles. Then it says how many molecules of KCl are decomposed, or sorry, KClO3. So again, we have the number of entities and moles and Avogadro's number. Capital. So the number of entities is moles times Na. We already have the KClO3 from part A is 0.02 moles. So you can see we did a lot of work in part A, but now we're flying, because so that question would be out of quite a few marks, and this would just be out of like 2. So that's a 23 there, Avogadro's number. Okay. For whatever reason, let me just see. Actually. Then in D, you guys don't have a spot, but if it's still on your sheet, I'm not even going to do a calculation here. So if we have the molecules of KCl, so I'm going to, the mole amount of KCl is the same as KClO3. Therefore, the number of entities is the same. Okay? And that is a perfectly reasonable answer. Okay, so let's do flow chart. So why do a flow chart? And again, maybe this isn't, maybe this isn't, something that you find useful. Then what I would do is don't even worry about it. Okay, so if you don't prefer flow charts, that's fine, but it can be helpful. So let's say we have some kind of, we'll keep the reaction simple, okay? A makes B. All right, so if we are given the mass of A, we can divide by the molecular weight or molar mass of A to get the moles of A, which is what we would have done in chapter 6. Now we want to change those moles of A into moles of B using a Stoich ratio. And then multiply by molecular weight to get the mass of B. So the example I did in this note was basically like this. You're given, if randomly A is the reactant, the reactant A goes to the moles of A, divide by molecular weight to get the moles of A. But you could do the same thing with the the product. So that's why I recommend that you do those questions that way, so you can organize your information. If it says, you were given this many grams, put those gram amounts there so that you can go backwards. Okay, so we went backwards, we went forwards, it doesn't matter. So then if you're given the mass of B, you can divide by molecular weight to get the moles of B, and then use a Stoic ratio to change them into moles of A, and then multiply by A's molar mass to get to the mass of A. Okay, so if that's helpful for you, I believe if you look at the formula sheet, I think it's on there as well. Maybe it'll help you. So when you're doing the homework, there is quite a bit. So I'm not going to post a new lesson until Tuesday, because I want you to do as many of these questions as possible, because limiting reagent and percent yield are basically applications of Stoic. Okay, so like I said, the worksheet sort of gets more work involved. The first one is just the mole ratio. Some of the questions on the worksheet you have to balance, some of them you don't. So make sure you're checking that. Same thing with the homework. There's a list of, like a checklist in the submodule. It's got the different types of questions, and then the last set will be them all mixed together. So